Hi, this is Anila. Today I am going to teach you metal and non-metal from physical science of class 8th. In the last part, we read about physical properties of metal and non-metal. Today, we'll learn about chemical properties of metal and non-metal. Before starting the new part, let's go for a revision of previous topic. Metals are generally hard, but sodium and potassium are soft in nature. Although mercury is metal, it is liquid. Diamond is an allotrope of carbon, which is a non-metal. It is the hardest material in the world. Generally, non-metals are either liquid or gas, but non-metal, bromine, is liquid. Mercury, gallium, sodium have low melting point. Although graphite is a non-metal, it is a good conductor of electricity. What we shall come to know after? Definition of chemical property, chemical properties of metal, chemical properties of non-metal, use of metal and non-metal, noble metal, use of noble metal. Key words to remember: metals, non-metals, chemical, amphoteric, carbon dioxide, hydrochloric acid, sulfuric acid, vigorous, rusting, copper hydroxide, copper carbonate. Now we'll discuss about chemical properties of metal and non-metal. In this part, we'll discuss reaction of metal and non-metal both with oxygen. Reaction of metal and non-metal both with water. Reaction of metal and non-metal both with acid, hydrochloric acid and sulfuric acid. Rusting of metal. Reaction of metal and non-metal both with metal salt. First, we should know what is chemical properties and why do we need to read it. Actually, physical properties are not sufficient to identify a compound. So, it is important to us to learn about the chemical property of matter. So, what is chemical property? Chemical properties are any of the properties of matter that can be observed and measured only by performing a chemical change or chemical reaction. Reaction of metal and non-metal both with oxygen. First, we'll know about the reaction with metal, then non-metal. Reaction of metal with oxygen. Metal oxides are formed when the metals react with oxygen. Let's take a magnesium ribbon and now burn it in the presence of oxygen. Look, it burns with light and flame of white color. Now take its ash and mixed with water in a test tube. Put a litmus paper into it. You can see that red litmus paper turns into blue. The oxide formed in this reaction is basic in nature because base turns red litmus blue. Reaction of non-metal with oxygen. When non-metals react with oxygen, they form the non-metal oxides. The nature of the non-metal oxides are either acidic or neutral in nature. A small amount of powdered sulfur in a deflagrating spoon is taken and heated. Look, sulfur starts burning. So, the spoon is introduced into a gas jar or gas tumbler. The tumbler is covered with a lid to ensure that the gas produced does not escape. The spoon is removed after some time. Now, a small quantity of water is added into the tumbler and quickly the lid is replaced. The tumbler is shaken well. The solution is checked with red litmus and blue litmus paper. Look, the solution of oxide turns the blue litmus red, which shows that the solution is acidic in nature. This also shows that oxide of non-metals is acidic in nature. So, one thing you have to remember. Metal oxides are usually basic in nature, but sometimes they also show amphoteric behavior as well. Amphoteric is a condition where the metal oxides can act as both acidic and basic in nature. Rusting of metals. Now we want to know about rusting. Rust is an iron oxide formed by a reaction of iron and oxygen where water or air moisture is present. Let's check the nature of rust formed as a result of the reaction between iron, oxygen, and water. A spoonful of rust is collected and dissolved in a very little amount of water. Look, the rust remains suspended in water. The suspension is shaken well. The solution is tested with red and blue litmus papers. The solution is basic in nature because it turns red litmus blue and there are no changes in the blue litmus. Does copper also get rusted? You can see a greenish deposit on the surface of copper vessels. When a copper vessel is exposed to moist air for long, it acquires a dull green coating. The green material is a mixture of copper hydroxide, that is CuOH whole twice, and copper carbonate, that is CuCO3. A 500 ml beaker or a big trough is taken and filled half of it with water. Sodium is taken, which is stored in kerosene, and keep it on a sheet of filter paper to blot the kerosene and cut a very small piece of sodium from it. The remaining sodium is put back again in kerosene. The sodium piece is put in water using forceps. Here you have to remember that you should maintain a distance from the beaker. Sodium metal is very reactive. It reacts vigorously with oxygen and water. A lot of heat is generated in the reaction. It is therefore stored in kerosene. You observed that sodium reacts vigorously with water. Some other metals do not do so. For example, iron reacts with water slowly. Generally, non-metals do not react with water, though they may be very reactive in air. Such non-metals are stored in water. For example, phosphorus is a very reactive non-metal. It catches fire if exposed to air. To prevent the contact of phosphorus with atmospheric oxygen, it is stored in water. Reaction with acid. All the samples are taken in 6 separate test tubes. Add 5 ml of dilute hydrochloric acid to each of the test tubes with the help of a dropper. Now observe the reactions. When magnesium, aluminium and iron react with diluted hydrochloric acid, hydrogen gas is evolved. The reaction will be rapid if more heat is applied. No reaction will happen for copper wire, charcoal and sulfur powder with diluted hydrochloric acid. When magnesium, aluminium and iron react with diluted sulfuric acid, hydrogen gas is evolved. The reaction will be fast if more heat is applied. No reaction will happen for copper wire, charcoal and sulfur powder with diluted sulfuric acid. Reaction with metal salt. Here you can see that we have taken 5 beakers with label A, B, C, D, E. Now we are adding 50 ml of water in each beaker. In first 2 beakers, A and B, we are adding a spatula full copper sulfate and stirring it to dissolve. In next 2 beakers, C and D, we are adding a spatula full zinc sulfate and stirring it to dissolve. In the last beaker, E, we are adding a spatula full iron sulfate and stirring it to dissolve. Zinc granules in beaker A, iron nails in beaker B, copper turnings in beaker C, iron nails in beaker D, copper turnings in beaker E. The blue color of copper sulfate disappears and a powdery red mass of copper is deposited at the bottom of the beaker A. In beaker B, red copper is found in the bottom of the beaker and on the nail, leaving light green iron sulfate solution. There is no change in C, D and E. In beaker A, zinc displaces copper from copper sulfate, giving rise to colorless zinc sulfate. Iron displaces copper from copper sulfate in beaker B, leaving light green color of iron sulfate. copper sulfate plus zinc equals to zinc sulfate plus copper. Copper sulfate plus iron equals to iron sulfate plus copper. Since we do not see any change in the other three beakers, that is C, D and E, we can infer that copper is unable to displace zinc from zinc sulfate. Iron is unable to displace zinc from zinc sulfate. Copper is unable to displace iron from iron sulfate.